You know that feeling, right? You've just written a piece of code and you are convinced it's the most efficient way to do something. But what if I told you that sometimes you can be completely outsmarted by your own compiler? Well, we're about to dive into a story just like that. It's a super common trap in performance testing, and it all starts with a classic developer debate between our two characters, Ethan and Eleanor.
Ah, and there it is, the voice of absolute certainty. This is Ethan, our junior developer. He's super enthusiastic, and he's just found what he's calling an objectively superior pattern. He really thinks he's cracked the code, found this brilliant shortcut. But as we're about to find out, sometimes the most clever path, well, it isn't always the fastest one.
So here's the scene. The whole thing kicks off during a pretty standard code review. The task? It's about as simple as it gets. Just join a prefix, user underscore, to a user ID. Ethan went with Go's strings.builder, and his logic seems totally solid. He's arguing it's gotta be faster, because it avoids all those extra memory allocations. And on paper, yeah, that makes perfect sense. But does it actually hold up in the real world? Okay, let's actually look at the code and break down Ethan's thinking. On the left, you've got his strings.builder approach. Now, you can think of this like grabbing a box that's already the right size before you start putting things in it. The theory is this is way more efficient. Then on the right, we have just simple string concatenation with a plus sign. This is the one we're often told is less efficient, right? It feels like you're making a whole new, bigger box every single time you add something. It's a classic best practice that just feels right. But then, in comes Eleanor, the senior engineer, and she just cuts right through all the talk with a serious reality check. Her point is simple but powerful. Performance isn't a philosophy. It's not about what feels right or what we think should be fast. It's a science. And the only way to really know for sure, you have to measure it. So the debate's over. It's time to get some real data. All right, so to settle this once and for all, they decide to use Go's built-in testing framework. I mean, this is the gold standard, right? They're going to write a proper benchmark, measure the performance right down to the nanosecond for each operation, and just let the cold, hard numbers tell them who's right. This should be it. A clear, definitive answer. And then the results come in. And they make 0 sense. The benchmark finishes in a blink, and just look at this table. Both methods, the builder and the simple plus sign, clock in at an identical 0.2 nanoseconds per operation. Let me put that in perspective for you. That is literally faster than it takes light to travel a couple of inches. It's not just fast, it's physically impossible. Something is very, very wrong here.
So this is the question that's just blowing Ethan's mind. I mean, how can they both take less than a billionth of a second? Even the absolute simplest stuff on a modern CPU takes some time. And for two totally different ways of doing things to have the exact same speed, the chances of that are, well, they're pretty much 0. So what in the world did they just measure? Because it sure wasn't their code.
But Eleanor, she's seen something like this before. She gets it. The problem isn't with the code they're trying to test. The problem is with the test itself. They've stumbled right into a classic textbook performance testing trap. And the culprit is a little surprising. It's the Go compiler, being way, way too smart for its own good. And here's the punchline. She tells him straight up, it deleted your code. See, the compiler is an absolutely ruthless optimizer. It looked at their benchmark, it saw that the string they were building, well, it was never actually used for anything, so it made a perfectly logical choice. It just got rid of the code completely. They weren't benchmarking string operations at all. They were benchmarking the speed of an empty loop. Ouch. This little trick the compiler pulls has a name, and it's called dead code elimination. It's a totally standard feature in pretty much any modern compiler. See, their whole job is to make the fastest possible program. And if they see some code that calculates a value, but that value is never, ever used, they just say, well, that's dead code, and poof, it's gone. In this case, Ethan and Eleanor got completely outsmarted by the compiler just doing its job a little too well. So this brings up a huge question, right? How do you actually measure your code if the compiler just keeps deleting it? Well, you have to play its game. You have to outsmart the optimizer. You need to find a way to trick the compiler into thinking that the result of your calculation is super important, that it's absolutely essential. That forces it to keep your code around. You've got to make that result live. And the solution is actually surprisingly simple. It's a classic trick, often called the global variable fix. Let's walk through it. First step, you declare a variable, but you do it outside the test function at the package level. Think of it like a public Dropbox that anyone can access. Step 2,
inside your benchmark loop, you do your calculation and you save the result to a temporary local variable. Then, and this is the key part, step 3, after the loop is all done, you take that local result and assign it to your global variable. This completely ties the compiler's hands. It can't possibly prove that some other piece of code somewhere else won't need that global variable later. So it has no choice. It has to keep your code and actually run the calculation. Okay, so with this little fix in place, they run the benchmark again. And this time, we get the real results. And wow, are they different. Ethan's supposedly superior strings.builder method, it clocks in at just over 5 nanoseconds. But the simple, old-school plus sign concatenation, a mere 1.3 nanoseconds. That is a massive difference. The so-called dumb way is almost 4 times faster for this specific task. So what gives? Why is this happening? Well, it all comes down to one word: context. Look, if you're doing something really complex, like building a giant string from a ton of different pieces inside a loop, strings.builder is absolutely the champion, no question. But for this really simple case, just sticking 2 strings together, the overhead of just setting up the strings.builder object is actually more work for the CPU than the super optimized simple plus sign operation. It just goes to show, a best practice is only best in the right situation.
So let's step back. What are the big lessons we can pull from this whole adventure? Because this story, it's about way more than just Go programming. It really gets to the heart of a fundamental rule in all of software engineering. You have to stop guessing and start measuring.
All right, let's just nail down these key lessons. First off, actually use the benchmarking tools that come with your language. They're there for a reason. Second, always remember that the compiler is this tricky wizard in the background. Its optimizations, especially something like dead code elimination, can totally give you fake results. Third, you got to know the tricks to beat it, like our little global variable fix, just to make sure you're actually testing what you think you're testing. And maybe the most important lesson of all, performance is all about context. With super fast in one scenario can be painfully slow in another. And that really brings us to the core principle, the lesson Eleanor taught Ethan, and the main takeaway for all of us. It's simple. Never guess, always measure. Your intuition? It's a great place to start, but it's not the finish line. When performance really matters, the only thing you can trust is hard data from a proper test. So, I'll leave you with a question to take back with you to your own code. What are the assumptions that are just hiding in plain sight in your projects? What best practices have you just been following on faith without ever actually testing them? Maybe it's time to stop guessing and start measuring.